Reactor development, like any heavy engineering development, is an inverted pyramid. At the apex of the pyramid is the original idea, supported by theory and a few experiments. But as the chosen system becomes an engineering and then a commercial reality, the resources required to carry out the development increase greatly.
New nuclear technologies, anyway, today are economically obsolete because of the risk, the financial risk. Investing in a reactor is like really gambling a very, very large amount of money. And if you build half a reactor, you have nothing.
Can a reactor be intrinsically safe and affordable?
Well, certainly some of the things that people say about the technology are correct. That light water reactors are vulnerable to meltdowns, that they have high pressure vessels, so that leads to some costs. There is waste disposal issue where you have fissile materials in the waste, where you have plutonium in the waste. And so in a molten salt reactor, you are operating at atmospheric pressure. You're generating your fissile materials ideally on site. And so they feel that there are many safety issues in the design. You drain the reactor in an emergency. And so I think that there are some strong advantages, but they only see the advantages. So I don't say there are not advantages compared to the present technology. But the system of actually the thorium reactor that has been proposed has never really been properly tested.
La grosse difficulté de ces systèmes passifs, c'est justement ça. Que dans la mesure où personne n'a à intervenir sur eux, la seule garantie de leur bon fonctionnement, c'est qu'ils aient été testés et validés dans les vraies conditions réelles dans lesquelles ils seront utilisés. Évidemment, pour un réacteur qui est nouveau, ces conditions réelles sont difficiles.
Tout ça, ce sont des petits tests indépendants, pas forcément très chers, qu'il faut mettre en place. Et donc, dans les quelques années qui viennent, on a besoin de quelques millions d'euros, entre 3, 4, 10 millions d'euros. On peut déjà démontrer beaucoup de choses. On peut aller très loin avec ça. L'étape d'après, un système grandeur réelle de circulation pour tester toutes les corrosions, les choses comme ça. Là, on est plutôt aux alentours de la centaine de millions d'euros. Donc ça commence déjà à être beaucoup plus cher. Il faut vraiment être sûr de ce qu'on fait, qu'on a une chance de pouvoir aboutir à quelque chose. Si on va sur le démonstrateur, là, on va taper sur le milliard d'euros.
That sounds like a lot of money. It is a lot of money. But in the economy that we're dealing with here, that's not much money at all. And Goldman Sachs, for example, had the company that was instrumental in screwing up the world's economy in 2008. In 2010, their bonuses were $16 billion. $16 billion with a B, which would have been enough to build, at that time, about 4 huge reactors that would produce clean energy for 60 years and employ hundreds and hundreds of people, paying it back, etc. So, when we're talking about money and investment, think of what money really means.
Donc là, il y a un véritable investissement, et cet investissement doit être finalement basé sur un choix politique. Est-ce qu'on veut investir le futur ou est-ce qu'on ne veut pas?
Sometimes the market economy or market force not necessarily drive you into the right direction. So we have to have the leadership, the wisdom, and long-term vision, perception to give the things like molten salt reactor technology development the support.
然后我们这个堆是从头做起，所以我们需要建立相关的实验室，去研究相关的科学问题和技术问题。经过4-5年的努力，我们现在在 CNAP 范围内，我们现在大概有400个员工和100多个研究生，以及一些退休然后再回来工作的年资比较深的一些科研人员，总共加起来大概有600人左右。
大家现在看到的这个回路正在进行升级改造，我们不停地对回路增加新的功能，做新的实验。那么这个回路是我们现在至少拥有的5个熔岩实验回路中间的一个。我们这每一个回路都有它特殊的用途，去做某一类的实验，验证某一类的理论。这么多的回路在一起，它构成了一个系统，使我们能够比较系统的去研究熔岩堆。这是我们现在拥有的一个独特的优势。
在我身边的这套装置是冷冻壁技术研究装置。这套装置的目的是解决我们熔岩堆研究过程中我们所发展的干法技术中的一个腐蚀问题。
66% of our primary energy came from coal. So China is still a coal-dominant energy consumption country, with only less than 10% accounts for non-fossil energy.
中国发展土基熔岩堆，目的是为了解决中国的能源和环境问题。
Every year, more than 3.5 million people are dying from the pollution from fossil fuels. That's 10,000 people per day. And we compare that with the effects of nuclear power. People are worried about the radiation, potential that radiation may be released. Well, there have been accidents, and they've killed a small number of people. But in 1 hour, the fossil fuels kill more people. And we need to understand the relative threats from the different energy sources.
If you look around the world, the only places where nuclear technology is succeeding is where it is pushed by the government, financed by the government, owned by the government. Here, where nuclear technology depends more on the marketplace to finance it, it cannot succeed.
If you want to make the case, make the proposition, there may be something to do which is really very different to what has been done before. It's more likely you'll get the support if you do that from a platform with a small business.
Alors, on est dans une époque où les gens essaient de développer beaucoup de choses autour du nucléaire. Il y a beaucoup d'idées, il y a surtout les petits réacteurs. Les gens essaient de modifier complètement le paradigme du nucléaire. Donc plein de gens ont des propositions, et en particulier des propositions dans le domaine des réacteurs à sel fondu.
IMSR, the integral molten salt reactor, fundamentally we've tried to simplify as much as possible, and that's crucial for shortening the research and development pathway and the regulatory burden. Things are completely passive safe that really will aid us in the regulatory pathway. There isn't a reason that things have to take 20, 30, 40 years. And we're a private company working with private investors, and we have to have that timeline realistic. Now, we're not exaggerating saying this is only going to take 3 or 4 years, but we do feel we can do it in under 10 years.
Indeed, there are many startups popping up in the field of the molten salt reactor. And at one hand, sometimes I think, well, maybe they are too early, because the molten salt reactor still needs a lot of development, in my view, in the chemistry field and materials field and the safety analysis field. But sometimes I also think, well, maybe they are right, and maybe the molten salt reactor is already much further ahead than I think.
Leur but n'est pas le même que le nôtre. Nous, on veut faire le réacteur qui résout tous les problèmes, quitte à dire qu'il ne fonctionnera que dans 50 ans. Eux, ils veulent un réacteur qui va fonctionner maintenant. Ça ne veut pas dire que c'est incompatible. Ils peuvent très bien construire des réacteurs, les faire fonctionner et montrer des choses qui nous intéressent du point de vue purement le sel, la gestion du sel, la gestion des matériaux, les pompes, les échangeurs, tout ça, ils peuvent le faire en faisant des réacteurs qui n'ont pas toutes les capacités qu'on aimerait qu'ils aient, mais ça ferait quand même avancer les choses.
So the main innovation of the IMSR is we plan to seal all the main components, the graphite, the heat exchangers, the pumps, into an integrated vessel, what we call our core unit. And that will not have a 30 to 60 year lifetime. It will only have roughly about a 7-year lifetime. But everything radioactive, everything that touches the radioactive fuel salt stays sealed in that reactor, and we'll use that for 7 years, and then it's replaced. Now that unit, we call it a core unit. That's what is in the sense the small modular reactor. It's what can be built in a factory, shipped on truck.
The way we do reactors today, they're so large and they operate under so much pressure that most of the structures have to be built on site. And that's led to many slowdowns in the development and construction of nuclear reactors. On the other hand, if we could build most of the parts in a factory and then ship them to a site with a minimum amount of preparation, then we'd be able to bring power online much more quickly.